There is a moment, somewhere in childhood, when death becomes real for the first time, not as a word, not as an abstract concept someone older mentioned once, but as a fact. You look at something that was alive, a bird, a pet, perhaps someone you loved, and you understand, with a quiet and irreversible certainty, that it is gone, that what was moving, breathing, present, is now simply not. And in that moment, without any formal education in biology or philosophy or physics, you form a belief that most people carry for the rest of their lives without ever questioning it. You believe you understand what death is. You believe it means ending. If this kind of question keeps you up at night, if you find yourself drawn to the deeper, stranger edges of science, consider subscribing and leaving a like. It helps more than you'd think, and there's a great deal more of this to come. That belief feels iron solid. It feels self-evident. It feels like the kind of thing that doesn't need a second look because every piece of experience you've ever had seems to confirm it. People die, animals die, stars eventually burn out, civilizations collapse into dust. Everything, it seems, has an expiry date printed somewhere in its nature. And when that date arrives, whatever was there becomes whatever is no longer there. And yet, the moment you sit down with the actual mathematics of the physical universe, not the comfortable, everyday approximations we use to get through Tuesday, but the real equations, the ones physicists use to describe reality at its most fundamental level, something profoundly strange becomes apparent. Death, as we imagine it, doesn't appear anywhere in the laws of physics, not as an event, not as a mechanism, not as a process that the universe sanctions or even acknowledges in the way our intuition assumes. You can search through classical mechanics, through thermodynamics, through general relativity, through quantum field theory, and what you will find, in every single case, is not a law of ending. You will find laws of transformation, laws of conservation, laws of continuous, unbroken evolution through time. The universe, as far as its own operating instructions are concerned, does not know how to stop. This is not a poetic overstatement. It is a precise scientific observation, and it is the thing that this video is really about. Let's begin with the most intuitive version of the problem, because the gap between what we experience and what physics describes becomes visible even at the most ordinary scale. Think about a candle flame. When a candle burns out, most people would say, without hesitation, that the flame is gone. It existed. Now it doesn't. Simple. But trace what actually happened, physically. The wax, a hydrocarbon compound, reacted with oxygen in the air. Chemical bonds broke and reformed. The carbon atoms that made up the wax are now CO2 molecules drifting into the atmosphere. The hydrogen atoms are now part of water vapor. The energy that was stored in those molecular bonds has been converted to heat and light and has radiated outward into the room, into the air, eventually into the broader thermal environment of the planet. Every atom that was in that candle is still somewhere. Every joule of energy that was in that candle is still somewhere. The flame didn't end. It dispersed. Now scale that observation up to a human being and hold it there for a moment, because this is where the comfortable story starts to creak. Your body is composed of roughly 7 octillion atoms, 7 followed by 27 zeros. Those atoms have been cycling through the universe for billions of years before they ended up organized, temporarily, into the specific structure that is you. The iron in your blood was forged in the core of a star that exploded before our solar system existed. The oxygen you're breathing right now has been inhaled and exhaled by countless organisms across hundreds of millions of years. The carbon in your cells has been part of ancient forests, deep ocean sediments, the bodies of creatures that no human eye has ever seen. None of that material started with you, and none of it ends with you. When a human body decomposes, whether through natural biological processes or cremation or any other mechanism, what happens is precisely what happened to the candle. The molecular bonds reorganize, the atoms redistribute, the energy converts and disperses, the carbon goes back into the soil, into the atmosphere, into other organisms. The calcium in your bones becomes part of the mineral substrate of the earth. Everything you are made of continues, in different configurations, in different contexts, through different stories. The matter doesn't end. The energy doesn't end. So when we say someone has died, what exactly are we saying has ended? At this point, a reasonable person might offer a clear answer. What ends, they'd say, is not the matter. Obviously, the matter persists. What ends is the organization of the matter, the specific, irreplaceable arrangement of atoms and molecules, and cells and neural connections that constituted a particular person. That arrangement dissolves, and it does not reassemble. That's the ending. That's what death is. And that answer is coherent. It is, arguably, the most scientifically defensible, popular account of what death means. But it has a problem embedded inside it that most people walk right past without noticing. If what dies is a pattern of organization, if what we're really mourning when someone dies is the dissolution of a specific information structure, then death becomes, at its core, an information problem, and information is not something the universe handles casually. This is where physics becomes genuinely unsettling. The laws of thermodynamics are among the most robustly established principles in all of science. They describe, at a fundamental level, how energy and matter behave in every system we've ever studied. And one of the things they tell us, through the concept of entropy, is that the universe relentlessly moves from ordered states toward disordered ones. Patterns dissolve, structures break down, complexity unwinds into simplicity. This is the thermodynamic story of death, and on its surface, it confirms our intuition. The ordered pattern that is a living human being becomes the disordered pattern of dispersed atoms and released heat. Entropy increases. The second law wins. Death, in this telling, is just physics doing what physics always does. But here is the question that this tidy account quietly suppresses. What happens to the information that described the pattern? In classical thermodynamics, this question didn't much matter, because classical physics treated information as a kind of secondary property, something we use to describe systems, not something the systems themselves are made of. But in the 20th century, that assumption was demolished. Claude Shannon, working at Bell Laboratories in the late 1940s, developed information theory, the mathematical framework that underlies every digital technology on Earth. What Shannon showed was that information is not just a description of physical systems. It has a precise, quantifiable relationship with the physical states of those systems. Information is physical. It is not separable from the matter and energy that carries it. And then quantum mechanics arrived with something even more radical. In the quantum world, the world of electrons, photons, quarks, and the fundamental fabric of reality, every particle, every system, every interaction is described by what physicists call a quantum state. This state contains the complete mathematical description of that system, its position, its momentum, its spin, every property it possesses, and every correlation it shares with every other quantum system it has ever interacted with. These quantum states evolve according to equations that are, at their mathematical core, perfectly reversible. Run them forward in time, and you get the future state of a system. Run them backward, and you recover the past state exactly without loss. This property is called unitarity, and it is not a minor technical detail. It is one of the deepest architectural features of quantum mechanics. What unitarity means, in plain terms, is that quantum information cannot be destroyed, ever, not in principle, not under any physical process that the universe permits. Every interaction, every transformation, every event, no matter how violent, how chaotic, how apparently irreversible, preserves the complete quantum information of the systems involved. The information might be scrambled almost beyond any practical possibility of recovery. It might be spread across a vast number of particles in a way that makes reconstruction essentially impossible. But it is there. It is conserved. The universe holds onto it. Now hold that principle next to a human being dying. The atoms of that person disperse. The molecules reorganize. The neurons stop firing. The specific electromagnetic patterns that corresponded to memories, personality, experience, consciousness, all of it unravels into what looks, from the outside, like thermal noise and biological matter returning to its component parts. But if quantum mechanics is correct, if unitarity truly holds, then somewhere, encoded in the quantum states of all those dispersed particles and radiated photons and redistributed molecules, is the complete information of that person, not metaphorically, not as a comforting abstraction, but as a real physical fact about the state of the universe. The pattern dissolved. But the description of the pattern at the deepest physical level persists, and nobody, not a single physicist, not a single philosopher, not a single person who has sat with this question, fully knows what to do with that. There is a deeper wrinkle here, and it is the one that most popular accounts of death quietly skip over, because it leads somewhere genuinely uncomfortable. We accept, intuitively, that death is a one-way gate. You go through it, and you do not come back. This intuition is reinforced by everything we observe. No one has returned from death to report on conditions. The biological processes of decomposition are irreversible under ordinary circumstances, and the thermodynamic arrow of time marches relentlessly in one direction. But here is what that intuition is built on: our experience of time. We perceive time as flowing forward. The past is fixed and inaccessible. The future is open and undetermined. The present is the thin blade between them where we exist. This experience feels so fundamental that we rarely think to question whether the universe shares it. It doesn't. The equations of fundamental physics, again, at every level from Newtonian mechanics to general relativity to quantum field theory, are time-symmetric. They work equally well in either direction. There is no arrow built into the mathematical laws of the universe. The asymmetry we experience, the sense of time flowing forward, the irreversibility of the past, emerges not from fundamental law, but from a statistical feature of the universe's initial conditions, and from the increase of entropy described by the second law. The physicist Sean Carroll, at Johns Hopkins, has spent significant portions of his career exploring what this means. In his framework, time's arrow is not a fundamental feature of reality. It is an emergent property of the particular low entropy state from which our universe began. In a universe that was not born in a state of extraordinarily low entropy or in regions beyond our observable horizon, there is no reason to expect time to flow in any particular direction at all. What this implies is that the absolute, irreversible finality of death, the sense that it represents a permanent, one-directional gate through time, may be an artifact of our particular vantage point inside a thermodynamically specific universe. It is not a fundamental truth. It is a feature of our circumstances, and our circumstances are not the whole of existence. By now, you might feel a particular kind of discomfort settling in, not the sharp discomfort of encountering a new and difficult idea, but something slower and more vertiginous, the discomfort of realizing that the ground beneath a certainty you have held your entire life is made of something softer than you thought. That is the precise feeling this kind of physics is designed to produce, not because physicists are trying to be provocative, but because reality, when examined with sufficient rigor, persistently refuses to conform to our expectations of it. The universe did not evolve to be intuitive. It did not arrange itself so that creatures with a lifespan of decades, living on a small rock orbiting an ordinary star, would find its deepest mechanisms immediately legible. What we are left with, at the end of this first pass through the problem, is something like this. Death, as a physical event, does not involve the destruction of matter. It does not involve the destruction of energy. It does not, according to quantum mechanics, involve the destruction of information. And it takes place within a universe whose fundamental laws contain no arrow of time, no mechanism of irreversible ending, no process that the equations themselves describe as final. What we call death appears to be, at the level of physics, a profound transformation, one of almost incomprehensible complexity, one that disperses and scrambles and reorganizes in ways that are practically irreversible, given everything we know about how to interact with the world. But transformation is not termination. The question this raises, and the question we have only just begun to circle, is not whether the matter ends. We have established that it doesn't. The question is whether something else does, something that cannot be captured by any equation currently in our possession, something that the physics points toward, obliquely and incompletely, without ever quite arriving, because matter is the easy part. Energy is the easy part. Even quantum information, for all its strangeness, fits inside a mathematical framework. What doesn't fit, what has never fit, despite a century of increasingly sophisticated attempts, is the experience of being alive. The fact that there is something it feels like to be you reading these words in this moment. The interior, subjective, undeniably real phenomenon of consciousness. Consider the ship of Theseus. It is one of the oldest philosophical puzzles in recorded history, and it goes like this. There is a ship, Theseus's ship, kept in a harbor as a monument. Over time, the wooden planks begin to rot. One by one, they are replaced with new timber. A plank here, a board there. The process continues, slowly, over many years, until every single piece of the original ship has been swapped out. Every nail, every beam, every plank of the hull. The question is simple and quietly devastating. Is it still the same ship? Most people find this question interesting, but not urgent. It feels like a thought experiment that applies to boats and perhaps to philosophical seminars. It does not feel like it applies to them personally, but it does. In fact, it applies to you with a precision and a literalness that should stop you cold, because you are the ship of Theseus, And the replacement is not a metaphor. The human body is not a fixed object. It presents itself as one. You look at your hands, and they appear stable, continuous, the same hands you had last year and the year before. But at the biochemical level, the body is engaged in a process of constant, radical self-replacement that makes Theseus's ship look like a minor renovation. The cells lining your stomach are replaced every 2 to 9 days. Your skin cells turn over in roughly 2 to 4 weeks. The red blood cells carrying oxygen through your body right now will be dead within 4 months, replaced entirely by new ones manufactured in your bone marrow. The cells of your liver, the organ responsible for filtering everything you consume, are replaced approximately every 12 to 18 months. Even your skeleton, which feels like the most permanent, structural part of you, is in a state of continuous remodeling. Bone cells called osteoclasts break down old bone tissue, and osteoblasts build new tissue in its place. In approximately 10 years, almost every atom in your skeleton will have been exchanged. The neuroscientist and author David Eagleman has described the body as less like a static thing and more like a river, a pattern that maintains its shape, while the water molecules that constitute it flow continuously through and onward. The form persists. The substance is always changing. But this raises a question that the river metaphor, elegant as it is, doesn't quite answer. If the matter is always changing, if the atoms are continuously being swapped out, the molecules replaced, the cells turned over, then what exactly is maintaining the pattern? What is holding the shape of the river while the water changes? And more unsettlingly, is whatever is maintaining that pattern the same thing as what you call you? To approach that question honestly, we need to think carefully about what kind of thing a pattern actually is. A pattern is not a substance. It is not made of any particular material. It is a set of relationships, a specific arrangement of components, defined not by what those components are made of, but by how they are organized relative to one another. The same pattern can, in principle, be instantiated in entirely different physical substrates. A melody doesn't care whether it's played on a piano, or a violin, or a digital synthesizer. The pattern, the sequence of notes, the intervals between them, the rhythm, is preserved regardless of the medium. This insight sits at the heart of a framework that has become increasingly influential in physics and cognitive science over the past several decades. The idea that information, not matter, is the fundamental currency of reality. Max Tegmark, a cosmologist at MIT and author of Our Mathematical Universe, argues for a position he calls the mathematical universe hypothesis, the proposition that physical reality is, at its deepest level, a mathematical structure, not described by mathematics, not modeled by mathematics, but is mathematics. In Tegmark's view, what exists is patterns, relationships, information, and the matter we perceive as solid, substantial, and primary is itself a manifestation of deeper mathematical structure. This is not a fringe position. It is a serious philosophical extrapolation from the trajectory of modern physics, which has, for over a century, progressively replaced intuitive, substance-based accounts of reality with formal, relational, information-based ones. Particles are not little billiard balls. They are excitations in quantum fields. Space-time is not a static backdrop. It is a dynamic geometry that responds to the distribution of energy and mass. Matter itself, at the level of particle physics, is increasingly described not as stuff, but as patterns of information encoded in quantum states. If that is what reality is made of, if the deepest layer of the physical world is informational, then what you are, at the most fundamental level, is not a collection of atoms. You are a pattern of information, a specific, extraordinarily complex arrangement of physical states that has been organized through billions of years of cosmic and biological evolution into something capable of experience, thought, memory, and self-reference. And this changes everything about how we think about death. Because if you are a pattern rather than a substance, then the relevant question is no longer what happens to the atoms when you die. We already know the answer to that. They disperse, they recombine, they continue. The relevant question becomes, what happens to the pattern? And here, the two great laws of thermodynamics enter the conversation in tension with each other. The first law tells us that energy is conserved. Nothing is created. Nothing is destroyed. Every joule that was in your body before death is in the universe after it, in a different form. The second law tells us something more uncomfortable. It tells us that entropy, the measure of disorder in a system, always increases. Organized, complex, low entropy structures do not spontaneously maintain themselves. Without a continuous input of energy, they degrade, they dissolve, they drift inevitably toward the most disordered state available to them. This is why you need to eat. It is why you need to sleep. The maintenance of the extraordinarily improbable pattern that is a living human body requires an unceasing expenditure of energy to hold entropy at bay. The moment that energy supply stops, the moment the metabolic processes that continuously repair and reorganize your biological structure cease, entropy begins to win. The pattern starts to unravel. And so, in thermodynamic terms, death appears to be entropy's final victory over pattern. The second law, patient and absolute, eventually dissolves every structure that the first law allowed to form. But there is a physicist who spent decades staring at exactly this point, at the apparent conflict between the conservation of energy and the dissolution of order, and who found something that neither law, on its own, had prepared him for. His name was Erwin Schrödinger, and in 1944, he wrote a small book that would change biology forever. Schrödinger was one of the architects of quantum mechanics, the man whose wave equation is to physics what Newton's laws are to classical mechanics. But in 1944, he turned his attention to a question that seemed almost embarrassingly simple compared to the abstract formalism of quantum theory. What is life? The book he wrote to answer that question, called What is Life, is one of the most consequential scientific texts of the 20th century. It directly inspired Francis Crick and James Watson in their pursuit of the structure of DNA. And it introduced a concept that cut right to the heart of what distinguishes living things from the inanimate matter they are made of. Schrödinger argued that living organisms are distinguished by their ability to feed on negative entropy, a concept he called negentropy, while the second law dictates that closed systems drift toward disorder. Living things are open systems. They take in energy from their environment, food, sunlight, and use it to maintain and increase their internal order while exporting entropy into the world around them. Life, in this framing, is a pattern that actively resists dissolution by continuously borrowing order from its surroundings. What this means is that the pattern that constitutes a living organism is not passively maintained. It is actively sustained, held together against the thermodynamic tendency toward disorder by the continuous work of metabolism, by the constant reading and executing of genetic information, by the relentless molecular machinery of the cell. And when that active sustaining process stops, when the organism can no longer feed on negentropy, the pattern does not simply freeze in place. It begins immediately to dissolve, because the laws of thermodynamics were always pressing against it, and the only thing holding them back was the ongoing work of life itself. This is, at one level, a poetic way of saying what everyone already knew, that bodies decompose. But Schrödinger's framing reveals something deeper. It reveals that life is not a thing that dies. Life is a process that stops, and what stops is not the matter, which continues, but the active, energy-consuming maintenance of a specific informational pattern. Death, in this view, is not an event that happens to you. It is the cessation of the process by which you happen. Now, we arrive at the question that makes this truly unsettling. If you are a pattern, a specific informational structure instantiated in biological matter, and if that pattern is defined not by its substance, but by its organization, then the following question becomes unavoidable. Could that pattern, in principle, exist in a different substrate? This is not a question about resurrection or science fiction. It is a question with a precise physical meaning. It asks whether the information that constitutes you, the specific arrangement of neural connections, synaptic weights, electrochemical gradients, and functional relationships that correspond to your memories, your personality, your cognitive architecture, is necessarily tied to the particular biological hardware you currently occupy, or whether it is, like a melody, substrate independent. The philosopher and cognitive scientist David Chalmers, in his work on the philosophy of mind, has argued for what he calls organizational invariance, the position that what matters for mental states is not the specific material implementation, but the abstract causal organization. If a system has the right functional relationships, the right patterns of information processing, it instantiates the same mental states, regardless of what it is physically made of. The neuroscientist Christoph Koch, who spent decades collaborating with Francis Crick on the search for the neural correlates of consciousness, has arrived at a related position through a different route. In his later work, particularly in The Feeling of Life Itself, 2019, Koch argues that consciousness is a property of certain kinds of information processing systems, a property that arises from the integrated, self-referential nature of the information patterns involved, rather than from anything specific about carbon-based biology. And Max Tegmark has gone further still, arguing in our mathematical universe that consciousness is, in principle, a pattern, a specific kind of information structure, and that the question of whether that pattern can be preserved, transferred, or reconstituted is not a question of metaphysics, but of physics. None of these thinkers are arguing that human consciousness can currently be uploaded, copied, or transferred. The technology for any such thing is inconceivably beyond anything we possess. What they are arguing is something more fundamental, that there is no obvious physical reason why it could not, in principle, be done. And that is a statement with consequences that reach far beyond technology. Because if you are a pattern, and if patterns are, in principle, substrate independent, then the question of what dies when you die becomes far more complicated than it first appeared. The matter continues. We established that, in Chapter 1, the energy continues. That is the first law, and it admits no exceptions. But now we are confronted with the possibility that the information of the pattern, the specific, irreplaceable arrangement of relationships and states that corresponds to your subjective experience of being you, is also, in some deep physical sense, not something that the universe is structured to simply delete. Not because of any mystical property of consciousness, not because of anything outside the laws of physics, but precisely because of the laws of physics. Quantum mechanics, as we began to explore in Chapter 1, describes reality through states that evolve in a perfectly information-preserving way. Every interaction encodes its history in the states of the systems involved. The universe, at its lowest level, is keeping a record of everything that has ever happened in it, not in any accessible registry, not in any form a living human being could read or recover, but encoded in the quantum correlations woven through the fabric of space-time. The pattern dissolves. The pattern disperses. The pattern becomes, practically speaking, irrecoverable beyond any technology we can imagine. But irrecoverable is not the same as destroyed. And in physics, that difference is not semantic. It is structural. It is written into the foundations of the theory. This is where the story shifts again. Because we have now established something that goes far beyond the original, comfortable account of death we began with. We began with the intuitive picture. Death ends things. We moved to the thermodynamic picture. Death disperses patterns, while conserving matter and energy. Now we are in a stranger place. We are in a picture where the information of the pattern is conserved too, not in any useful form, not in any form that matters to the person who has died, but conserved nonetheless, preserved in the quantum architecture of a universe that does not, at its most fundamental level, know how to delete. And this raises a question that we have been carefully approaching but have not yet directly asked. If information is conserved, if your quantum description persists somewhere in the state of the universe after your death, what is it exactly that makes that different from being alive? The obvious answer is consciousness, the subjective experience, the interior light that turns a pattern of information into something that feels like something from the inside. But here's the problem. Physics has no account of that light, not even a preliminary one. The equations describe the pattern. They describe the information. They describe the states and their evolution. But nowhere in any equation, in any theory, in any framework, is there a term for the experience of being that pattern. That absence is not a gap that physics has simply not gotten around to filling. It is a recognized, formally named, deeply contested problem that sits at the boundary of neuroscience, physics, and philosophy. And it has a name: the hard problem of consciousness. Imagine writing a letter, a long one. Every memory you have ever formed, every preference you have developed, every fear, every moment of recognition, every face you have loved, and every idea that has kept you awake at night. You write it all down, fold it carefully, seal it inside an envelope, and then drop it into a fire. The paper burns. The ink combusts. The envelope collapses into ash. Smoke rises and disperses into the air. From any practical standpoint, the letter is gone. Irretrievably, completely, permanently gone. Now imagine being told that the letter is not gone, that every word, every sentence, every thought you committed to that page is still encoded somewhere, not in any form you could read, not in any form any technology we possess could recover, but present nonetheless, written in the only language the universe actually speaks. That is not a philosophical consolation. That is, if the current best understanding of quantum mechanics is correct, a precise, physical description of what happened. The universe does not burn letters. it encrypts them. To understand why physicists believe this and why it matters so profoundly to the question of death, we need to travel to one of the strangest places the human mind has ever tried to follow: the edge of a black hole. In 1974, Stephen Hawking published a calculation that produced one of the most celebrated and, simultaneously, most troubling results in the history of theoretical physics. Working at the intersection of quantum mechanics and general relativity, two theories that had stubbornly refused to be unified, Hawking showed that black holes are not, in fact, perfectly black. Quantum effects at the event horizon, the boundary beyond which nothing can escape a black hole's gravitational pull, cause the black hole to emit a slow, steady trickle of thermal radiation. This radiation, which became known as Hawking radiation, carries energy away from the black hole. And because energy and mass are equivalent, as Einstein showed us, the black hole slowly loses mass as it radiates. Over inconceivable spans of time, it shrinks, it grows dimmer, and eventually, it evaporates entirely, leaving behind nothing but a faint residue of thermal radiation dispersed through the surrounding space. This was a stunning result. It was the first concrete theoretical bridge between quantum mechanics and gravity, and it earned Hawking a fame among physicists that few scientists of any era have matched. But buried inside this beautiful result was a catastrophe. Think about what a black hole is. Physically, it forms when a massive star, or an accumulating mass of any kind, collapses under its own gravity to a point of extreme density. Everything that falls into a black hole carries information with it. The specific quantum states of every atom, every particle, every photon that crosses the event horizon is information about what that object was, its composition, its history, the complete record of its physical states. All of that information falls in. The black hole grows. And then, according to Hawking's calculation, the black hole slowly evaporates, radiating energy in the form of thermal radiation. Here is the problem. Thermal radiation is, by definition, featureless. It carries no specific information about the matter that produced it, the way a fire's heat carries no specific information about the letter that was burned. If the black hole evaporates completely into thermal radiation, then all the information that fell into it, all the quantum states, all the physical histories, has apparently vanished, not dispersed, not encrypted, destroyed. And that is something quantum mechanics says cannot happen. The principle at stake is called unitarity, and it is not a minor technical postulate. It is one of the foundational architectural commitments of quantum theory, the principle that the mathematical evolution of quantum states is perfectly reversible. Run any quantum process forward, and you get the future state. Run it backward, and you recover the past state, exactly, without loss. No information is ever created. No information is ever destroyed. Unitarity is not just a feature of quantum mechanics. It is, in a deep sense, what quantum mechanics is. Remove it, and the entire mathematical structure of the theory, the probability calculus that underlies every prediction quantum mechanics has ever made, every experiment it has ever correctly described, begins to fall apart. So Hawking's calculation placed physics on the edge of a knife. Either general relativity was wrong about what happens at the event horizon of a black hole, or quantum mechanics was wrong about the indestructibility of information. Both theories were extraordinarily well confirmed by experiment. Both had earned their authority across decades of precise, successful prediction. and they were telling contradictory stories about the same event. This became known as the black hole information paradox, and for roughly 3 decades, it was one of the most bitterly contested problems in theoretical physics. The physicist who took it most personally was Leonard Susskind. Susskind, a theoretical physicist at Stanford University and one of the architects of string theory, found Hawking's willingness to accept the destruction of information not just wrong, but philosophically intolerable. In his account of the debate, laid out in his book The Black Hole War, 2008, Susskind describes a confrontation with Hawking at a private conference in San Francisco in 1983 that marked the beginning of a nearly 20-year intellectual battle. Hawking's position was stark. Information falls into the black hole and is lost when the black hole evaporates. Quantum mechanics, in this extreme circumstance, breaks down. The universe does not, after all, keep perfect records. Susskind's position was equally stark. That conclusion is impossible. If information can be destroyed, then quantum mechanics, and by extension, our entire account of physical reality, is fundamentally broken. Something in our understanding of black holes must be wrong, but it cannot be unitarity. The resolution, partial, contested, still not fully formalized, began to emerge in the 1990s through the work of two physicists, Gerard 't Hooft and Juan Maldacena. Gerard 't Hooft, a Dutch theoretical physicist who shared the 1999 Nobel Prize in Physics, proposed something that, when you first encounter it, sounds more like mysticism than science. He suggested that the information content of everything inside a black hole, every particle, every quantum state, every physical detail of all the matter that has ever crossed the event horizon, is entirely encoded on the two-dimensional surface of the event horizon itself. Not a copy, not a summary, a complete, exact encoding. This is the holographic principle, the idea that the information describing a three-dimensional region of space can be fully represented on a two-dimensional boundary surrounding it, like a hologram, where a three-dimensional image is encoded in the interference patterns on a two-dimensional photographic plate. The volume of space inside a black hole is, informationally speaking, a projection of its surface. Then, in 1997, Juan Maldacena, at the Institute for Advanced Study in Princeton, published a paper that transformed this conjecture into something approaching a mathematical proof. Working within string theory, Maldacena showed a precise, formal equivalence between a theory of gravity operating in a region of space and a quantum field theory operating on the boundary of that region, with no gravity at all. This correspondence, known as the ADS-CFT duality, or more colloquially as the Maldacena duality, is now the most cited paper in the history of high-energy physics. It doesn't just suggest that information is preserved in black hole evaporation. It provides a concrete mathematical framework in which that preservation can, in principle, be demonstrated. Hawking himself eventually conceded the point. In 2004, at a conference in Dublin, he publicly announced that he had been wrong, that information is not destroyed in black holes, that it escapes, encoded in the correlations of Hawking radiation in a form that is extraordinarily scrambled, but nonetheless present, nonetheless recoverable in principle. The universe, it appears, does not destroy information, not even in the most violent, extreme environments it can produce. Now step back from black holes entirely. Step back from event horizons and Hawking radiation and holographic principles, and return to something far more personal. Return to a human being dying. The atoms disperse, the molecules reorganize, the pattern that was a living person dissolves into its constituent parts, which are distributed through the biological and physical environment into the soil, the air, the water, the bodies of other organisms, the slow thermal exchange of energy with the surrounding world. And at every step of this process, at every interaction, every chemical reaction, every quantum event involved in that dissolution, the information of those interactions is encoded in the quantum states of the systems involved, not legibly, not in any form that resembles the original, but encoded, because that is what quantum mechanics says always happens. Every atom that leaves your body carries, in its quantum state, the history of every interaction it experienced while it was part of you. Every photon radiated by the heat of your decomposing cells carries correlations that, in principle, link it to the state of the system from which it came. The information doesn't gather itself neatly somewhere for safekeeping. It fans out across the universe in a cascade of correlations so complex, so diffuse, so entangled with everything else that no conceivable technology could ever reconstruct it. But it is there, in the same way that the information in Hawking's burning letter is encoded in the quantum states of the smoke and the ash and the thermal radiation and the air currents in the room. Irrecoverable, yes, but present. The information of a human being who has died is encoded, distributed, scrambled through the quantum fabric of the universe. This is what unitarity means for death. Death does not delete, death encrypts. The physicist and author Carlo Rovelli, in his book The Order of Time, 2018, offers a meditation on memory that arrives at a related truth from a different direction. Rovelli observes that what we call the past is not, in any physical sense, gone. It is simply no longer accessible from our current location in time. The events that have occurred are encoded in the present state of the universe, in the arrangement of matter, in the distribution of energy, in the precise configuration of every quantum state that resulted from every event that has ever happened. The past, in Rovelli's framing, is written in the present, not metaphorically, physically. The current state of every particle in the universe carries, encoded in its quantum correlations, the history of every interaction that particle has ever had, all the way back to the beginning of time itself. We cannot read that history. The decoding problem is beyond anything imaginable, but the information is there because it was never removed. And if that is true of everything that has ever happened in the universe, if the Big Bang itself is still, in some encoded form, present in the current state of reality, then the question of whether a human being who has died has truly ended becomes genuinely ambiguous in a way that physics has not fully resolved. There is a name for the quantity that measures the information content of a quantum system. It is called von Neumann entropy, after the mathematician John von Neumann, who first formalized it in the 1930s. And one of the things that quantum mechanics tells us about von Neumann entropy is that it is conserved across unitary evolution, which means that the total information content of a closed quantum system, like, in the relevant limit, the universe itself, never changes. Not when stars form, not when they explode, not when black holes evaporate, not when living things die. The universe began with a certain quantity of information, and it will end, if it ends, with exactly the same quantity. What changes is the distribution of that information, the accessibility of it, the form in which it is encoded. Complexity builds, then dissipates. Patterns form, then dissolve. Order emerges from lower entropy states, then disperses into higher entropy ones. But the total information, the von Neumann entropy of the universe as a whole, remains constant. You are, in this framing, not something the universe loses when you die. You are something it redistributes, and yet, that redistributed information, that scrambled, diffused, irrecoverable encoding of what you were, does not experience anything. It does not think. It does not feel. It does not know that it was once part of something that looked out at the night sky and felt small and curious and alive. Or does it? This is the question that quantum information theory, for all its mathematical precision, cannot answer. The conservation of information tells us that the description of a physical system is never lost. It tells us nothing about whether that description, in any form or configuration, is accompanied by experience. The hard problem of consciousness, the question of why any physical process gives rise to subjective experience at all, is not a problem that unitarity solves. It is a problem that unitarity makes sharper, because now we know that the information persists. Now we know the universe keeps the record. What we do not know is whether keeping the record is the same as keeping the light on. And there is one corner of physics that has looked directly at that question, at the relationship between observation, information, and the existence of a conscious witness, and come back with an answer that is more disturbing than any of the territory we have covered so far. That corner is quantum measurement theory, and the question it raises is one that should genuinely unsettle you, not because it suggests that death is something other than what we think it is, but because it suggests that the universe, at the level of its own operating logic, may require something like you to exist at all. There is an experiment so simple that it can be described in a single sentence, and so disturbing that it has occupied the greatest minds in physics for nearly a century without being fully resolved. Fire a single particle, an electron, a photon, it doesn't matter, at a barrier with two narrow slits cut into it. Behind the barrier, place a screen that records where the particle lands. If the particle is a particle, a small, definite, localized thing traveling in a single direction, it should pass through one slit or the other and leave a single mark on the screen, the way a bullet fired at a fence would pass through one gap and embed itself in the wall behind. That is not what happens. What happens instead is that the particle, traveling alone with nothing else in the experiment, passes through both slits simultaneously. It interferes with itself, the way a wave does, creating a pattern of alternating bright and dark bands on the screen. A perfect interference pattern, the unmistakable signature of a wave phenomenon. The particle, somehow, is behaving like a wave. But then something stranger happens. If you add a detector, any detector of any kind, even one that is entirely passive, to determine which slit the particle actually went through, the interference pattern disappears. The U particle suddenly behaves like a particle again. It goes through one slit, leaves one mark, and nothing about it suggests it was ever a wave at all. The act of observation, the mere presence of a measuring device, has changed the physical behavior of the particle, not influenced it, not disturbed it, changed it. And in that single experimental result lies a problem about the nature of reality, the role of the observer, and the meaning of death that no physicist has yet solved. The standard interpretation of quantum mechanics, the one still taught in most university physics courses, the one that Niels Bohr and Werner Heisenberg assembled in Copenhagen in the late 1920s, accepts this result without attempting to fully explain it. In the Copenhagen interpretation, a quantum system exists in a superposition of all its possible states until it is measured. The wave function, the mathematical object that describes those possibilities and their probabilities, does not describe where the particle is. It describes where the particle might be found. When a measurement occurs, the wave function collapses. The range of possibilities resolves into a single actuality. The particle is found here, not there. The superposition ends. Reality, in some precise but deeply unclear sense, crystallizes. This collapse is not described by the Schrödinger equation, the equation that governs how wave functions evolve through time. The Schrödinger equation is smooth, continuous, and perfectly reversible. Wave function collapse is instantaneous, discontinuous, and irreversible. They are governed by entirely different rules, and quantum mechanics applies one set of rules to the quantum world and another set to the act of measurement, without ever fully explaining what measurement actually is or precisely when collapse occurs. This is called the measurement problem, and it is not a solved problem. It is one of the deepest unsolved problems in the foundations of physics. After 100 years of quantum mechanics, after technologies built on its predictions have transformed every aspect of human civilization, we still do not have a universally agreed account of what happens when someone looks at something. The mathematician and physicist John von Neumann, the same figure whose entropy formula we encountered in Chapter 3, attempted to formalize the measurement problem in his 1932 treatise, Mathematical Foundations of Quantum Mechanics, and in doing so, he set off a chain of reasoning that leads somewhere genuinely vertiginous. Von Neumann's analysis showed that the boundary between the quantum system and the measuring device is not fixed. You can push it. If you treat the measuring device itself as a quantum system, as, of course it is, being made of atoms governed by quantum mechanics, then the device and the particle become entangled. They enter a joint superposition. The collapse hasn't happened yet. It just involves a larger system. So you add a second measuring device to observe the first. Same problem. The second device becomes entangled too. The superposition grows. You can keep extending this chain indefinitely, device after device, observer after observer, and at each step, the quantum description simply absorbs the new element into an ever larger superposition without collapsing. Von Neumann concluded that the chain terminates only at one place. Only one element in the measurement chain is, by its nature, not a physical object that can itself be treated as a quantum system. Consciousness. In von Neumann's analysis, the wave function collapses when the information enters the awareness of a conscious observer, not when it hits the detector, not when it is recorded on a hard drive, when a mind knows the result. This is a conclusion that makes most physicists deeply uncomfortable, and for understandable reasons. It seems to smuggle something non-physical, something irreducibly subjective, into the foundations of a supposedly objective scientific theory. It seems to make the universe depend on being looked at, which sounds, frankly, absurd. But the discomfort of a conclusion is not an argument against it, and several serious physicists have followed von Neumann's logic further than he himself went, to places that the discomfort becomes irrelevant, because the strangeness has simply overwhelmed it. One of them was Eugene Wigner. Wigner was among the most distinguished theoretical physicists of the 20th century, a Nobel laureate, a pioneer of quantum symmetry theory, a figure of enormous technical authority, and in 1961, he published a thought experiment that remains to this day one of the most provocative in the history of physics. He called it the paradox of Wigner's friend. The setup is deceptively simple. Wigner's friend is inside a sealed laboratory performing a quantum measurement, say, measuring the spin of an electron that is in a superposition of up and down. From inside the laboratory, the friend makes the measurement and gets a result. The superposition has collapsed. The friend knows whether the spin was up or down, but Wigner himself is outside the laboratory. He has had no access to the result. From his perspective, the laboratory is a closed quantum system, and nothing has yet caused the wave function to collapse. The friend, the measuring device, and the electron are all still, from Wigner's external vantage point, in a superposition of all possible outcomes. Two observers, two irreconcilable descriptions of the same physical reality, both valid according to quantum mechanics, both internally consistent and utterly incompatible with each other. Wigner used this thought experiment to argue that consciousness must play a special role in quantum mechanics, that a physical observer capable of subjective experience draws a hard boundary that the Schrödinger equation cannot cross, and that this boundary is what actually causes collapse. Most physicists of his era found this conclusion extravagant. Most physicists of our era are no longer so certain. In 2019, a team of researchers led by Massimiliano Proietti at Heriot-Watt University in Edinburgh conducted an experiment that transformed Wigner's thought experiment from a philosophical puzzle into an empirical test, using pairs of entangled photons and two independent measuring stations, each acting as a separate observer in the Wigner's friend framework. The team demonstrated that the predictions of standard quantum mechanics, when applied to the observers themselves as quantum systems, lead to observably different outcomes than if observers are treated as classical recorders. Their results were consistent with the quantum mechanical prediction, which means the incompatibility between different observers' accounts of the same quantum event is not merely a philosophical anomaly, it is a measurable physical fact. The physicist Czeslaw Bruckner at the University of Vienna, who developed the theoretical framework underlying this experiment, has argued that the results imply something stark. There is no single, observer-independent account of quantum events. Reality, at the quantum level, does not have one description that all observers share. It has a description relative to each observer, and those descriptions can be, and in the experiment were demonstrated to be, mutually inconsistent. This is not a small philosophical adjustment. It is a fundamental challenge to the idea that there is an objective reality out there, unfolding the same way for everyone, independent of who is watching. And if that is the nature of quantum reality, if the universe's events are, in some deep sense, observer relative, then the death of an observer is not a neutral event. It is not simply the cessation of a recording device. It is the disappearance of a perspective from which a particular slice of quantum reality had a definite description. What happens to that slice of reality when the perspective it was relative to is gone? This question was taken further than anyone else dared by the physicist John Archibald Wheeler, one of the towering figures of 20th century physics, the man who coined the terms black hole and quantum foam, and the doctoral supervisor of both Richard Feynman and Hugh Everett. Wheeler spent the latter decades of his career developing what he called the participatory universe, a framework in which the universe is not a pre-existing stage on which observers happen to be present, but a structure that is, in a deep and irreducible sense, brought into being by observation. His most radical formulation of this idea was expressed in a phrase he returned to again and again in his final years: it from bit. The idea is precisely what it sounds like. Every particle, every field, every dimension of space-time, every it in the physical universe derives its existence, its properties, its reality from information, from answers to yes or no questions, from bits. The universe, in Wheeler's vision, is not made of matter that happens to carry information. It is made of information that happens to manifest as matter. Wheeler's participatory universe went further still. Drawing on the peculiarities of quantum measurement, he proposed what he called the delayed choice experiment, a variation of the double-slit experiment in which the decision of whether to measure which slit the particle goes through is made after the particle has already passed through the barrier. The results are exactly as strange as they sound. The particle's past behavior, whether it behaved as a wave or a particle at the moment it encountered the slits, appears to be determined by a measurement choice made in the future. The act of observation reaches backward in time and shapes what already happened. Wheeler drew from this a conclusion that feels almost too large to hold: that observers are not incidental features of the universe. They are, in some sense, co-creators of it, that the universe, across its entire history, has been calling observers into existence in order to give itself a definite past. This is speculative. Wheeler himself was careful to distinguish it from established physics, but it is speculative in the way that certain ideas are speculative, not because they are unserious, but because they are ahead of the tools available to confirm or refute them. Now hold all of this against the fact of death and feel the specific quality of discomfort it produces. If observers participate, even partially, in the determination of quantum reality, if the presence of a conscious perspective shapes, in any meaningful sense, the physical description of events, then the removal of that observer is not simply a biological event. It is a change in the structure of what is physically real, at least within the domain of reality that was observer relative. The quantum states that, from your perspective, have definite values, the specific outcomes of measurements you have made, the photons your retinas have absorbed, and your brain has processed into experience. The entire accumulated history of definite events that constitutes your life are definite, in part, because you were there to make them so. After you are gone, those outcomes still occurred. The information is still encoded in the universe, as we established in Chapter 3. But the perspective from which they were definite, from which they were real in the most immediate sense, has dissolved. What remains is the encrypted record. What is gone is the reader, or so it appears. Because there is one interpretation of quantum mechanics that removes this problem entirely, one framework that does not require wave function collapse, does not assign a special role to consciousness, does not produce incompatible observer-relative descriptions, and does not leave the universe dependent on being witnessed. It is an interpretation that solves the measurement problem cleanly, elegantly, and completely by proposing something so radical that most people, when they first encounter it, assume it must be wrong simply because it is too large to be true. It proposes that the wave function never collapses, that every possible outcome of every quantum event actually occurs, that the universe, at every moment, branches into every version of itself that quantum mechanics permits, and that every one of those branches, every world, Every version of every observer, every path that quantum probability has ever opened is equally, completely, and permanently real. Hugh Everett III proposed this in 1957. He called it the relative state formulation. We now call it many worlds, and what it implies about death is something that should make you sit very still for a moment. In the winter of 1954, a 24-year-old graduate student at Princeton sat down and began writing a paper that would either revolutionize physics or be quietly ignored. He suspected, with the particular clarity that occasionally visits young minds, before the world has had sufficient time to complicate them, that both outcomes were equally likely. His name was Hugh Everett III. His supervisor was John Wheeler, the same Wheeler who would later speak of a participatory universe and the idea that reality requires an observer to crystallize into being. And the paper Everett was writing proposed something so enormous, so structurally radical, that most of the physicists who read it in 1957, when it was finally published, simply declined to take it seriously. Everett's idea was this: the wave function never collapses, not under measurement, not under observation, not ever. The Schrödinger equation, which governs the evolution of quantum states, is always valid. Always. Without exception. Without the additional collapse postulate that Copenhagen appended to the theory. Without the special role for consciousness that von Neumann suggested. Without any of the patching and supplementing that physicists had been doing for 3 decades to make quantum mechanics safe for human intuition. If you take the Schrödinger equation seriously, if you apply it consistently and universally, the way you would apply any other fundamental law of physics, then what it tells you is not that superpositions collapse when observed. It tells you that the observer becomes part of the superposition, that the measuring device, the laboratory, the physicist, and the entire environment all become entangled with the system being measured, and together they evolve into a superposition of every possible outcome simultaneously. Every outcome occurs, all of them, at once, in parallel branches of a single universal wave function that never stops growing. This is the many worlds interpretation, and if it is correct, it does not merely change our understanding of quantum mechanics. It changes what it means to exist. It changes what it means to choose. It changes what death is. It may, in fact, make death impossible, and not in any way that feels like a comfort. To understand what many worlds actually claims, it helps to start with something small, not with universes or cosmological scales, but with a single quantum event. An unstable atomic nucleus sits in isolation. Quantum mechanics tells us it has, say, a 50% probability of decaying in the next hour. In the Copenhagen interpretation, at the end of that hour, one of two things has happened. It has decayed, or it has not. The wave function, upon measurement, collapsed into one of those outcomes. In Everett's framework, both things have happened. The universe has branched. In one branch, the nucleus has decayed. In another, it hasn't. Both branches are equally real. Both branches contain an observer who measured the nucleus and found a definite result. Neither observer is aware of the other. Neither branch has any access to what occurred in its counterpart. But both exist as distinct, parallel, equally valid instantiations of the universal wave function. Now consider that this branching does not happen once an hour in one isolated nucleus. Quantum events of this kind occur constantly at every scale of physical reality, billions upon billions of times every second, in every cubic centimeter of the universe. every particle interaction, every photon absorbed by a molecule of chlorophyll in a leaf, every electron tunneling through a protein in a cell membrane, every firing of every synapse in every nervous system on Earth. At each of these events, in Everett's framework, the universe branches. The number of branches is not merely large, it is incomprehensible. It exceeds any quantity for which human language has a name. And in every single one of those branches, every version of every observer that quantum mechanics permits continues to exist. The reason we do not experience this branching, the reason it feels, from the inside, as though only one outcome occurs, is explained by a process called decoherence. When a quantum system interacts with its environment, with air molecules, with photons, with the vast and complex physical surroundings of any real-world measurement, the quantum coherence between its possible states is destroyed almost instantaneously. The interference between branches becomes suppressed beyond any practical possibility of detection. The branches, which in principle remain part of the same universal wave function, become, for all observable purposes, completely isolated from one another. This is decoherence, and it was first rigorously developed by the physicist Wojciech Zurek at Los Alamos National Laboratory in the 1980s and 1990s. Zurek showed that the apparent definiteness of the classical world we experience, the fact that we see cats as either alive or dead, not both, emerges naturally from the interaction of quantum systems with their environments, without requiring any collapse postulate, without requiring consciousness to play a special role. The branches don't need to communicate with each other. They don't need to be aware of each other. They simply become, through decoherence, physically inaccessible to one another, as separate and unreachable as regions of space beyond the cosmological horizon. Each branch is its own world. Each world contains its own observers, and each observer, embedded in their branch, experiences a single, definite, classical-seeming reality, never knowing, never able to know, that they are one version among an unimaginable multitude. Now consider what this means for death. At every moment of your life, quantum events are occurring inside you and around you. Your neurons fire based on electrochemical processes that, at the molecular level, involve quantum tunneling. The DNA in your cells undergoes quantum fluctuations. The photons entering your eyes trigger quantum transitions in your retinal proteins. Every breath, every heartbeat, every thought involves quantum events whose outcomes, in the many worlds framework, branch the universe. And at every branching, there is a version of you in each branch. Now consider the moments that came closest to ending your life. The car that turned a second before you stepped off the curb. The illness that resolved. The 1,000 random biological processes that, had they gone slightly differently, would have terminated your existence. At each of those moments, the quantum events underlying the physical processes involved had multiple possible outcomes. In some branches, the outcome was lethal. In those branches, you died. But you are not in those branches. You are here, reading this, which means you are, by definition, in a branch where all of those potentially lethal events resolved in the direction of your survival. Not because you were lucky. Luck is not a concept with explanatory power in many worlds, but because in the branches where you did not survive, there is no version of you to be the reader of this sentence. Your subjective experience can only ever be located in a branch where you exist to have it. This is the anthropic logic that underlies what the physicist Max Tegmark has called quantum immortality, a term that sounds hyperbolic and is not. The argument was first proposed seriously by the philosopher and physicist Hans Moravec in 1987 and was later formalized and popularized by Tegmark. It runs like this. In the many worlds framework, every quantum event branches reality into all possible outcomes. Among those outcomes, at every moment, are branches in which you die and branches in which you survive. As the branches multiply, as the tree of reality grows outward through time, the branches in which you have survived to the present moment become, statistically, a smaller and smaller fraction of the total. But they never reach zero. There is always, in principle, a branch in which the sequence of quantum events has conspired to keep you alive, a branch in which the cancer cell failed to divide, in which the neurological event resolved, in which the accident didn't happen. The probability of finding yourself in such a branch from a third-person view becomes vanishingly small as time goes on. But from a first-person view, from the only view you actually have, the probability is always 100%. You can only ever find yourself alive, which means, if many worlds is correct, that from your subjective perspective, you will always find yourself surviving, not indefinitely in any single branch. Most branches end your life at some point, and those endings are real in those branches. But your first-person experience, your continuous thread of subjective observation, will always find itself in the branch where you survived the last event that might have killed you, and the one before that, and the one before that, all the way back to the beginning. You will grow old in the branches where you survive long enough. You will become, improbably, ancient. You will find yourself, eventually, in a branch where some remarkable accident of biology or technology has extended your life far beyond any normal span. And eventually, you will find yourself in branches that are vanishingly unlikely by any external measure. The one in a trillion confluence of events that kept this particular pattern of information assembled and functioning while the universe aged around it. And in all of those branches, from the inside, your experience will feel completely normal, because the branches that felt abnormal, the ones where something went wrong, are the branches you are not in. Sit with that for a moment, because it is not a comfortable idea. Quantum immortality, when you follow it to its logical conclusion, is not a vision of eternal bliss. It is something far stranger, and in certain lights, far more troubling. Consider what it means to age in the branches where you survive longest. The you that finds itself still alive at 120 does so in a body that has accumulated a century and more of cellular damage, tissue degradation, and systemic decline. The branches that permit your survival at such ages are not branches where you are spared suffering. They are branches where the quantum events happened to run in the direction of survival despite everything else going wrong. The suffering continues. The deterioration continues. Only the final threshold is never crossed, and the branches become increasingly improbable. The version of you that survives to 300 years old exists in a branch so statistically remote from anything we would call normal physical reality that the world around it bears little resemblance to anything familiar. Not because the laws of physics have changed, but because the specific sequence of extraordinarily unlikely quantum outcomes necessary to sustain your survival has, in the process of occurring, shaped the environment in ways that diverge more and more radically from the most probable state of the universe. The philosopher David Lewis, who developed the framework of modal realism, the philosophical counterpart to many worlds, described this with unsettling clarity. In the space of all possible worlds, the worlds that contain your continued existence become progressively stranger, progressively more improbable, progressively further from anything that feels like home. This is quantum immortality, not paradise, not peace, a continuous thread of first-person survival through an increasingly alien landscape of improbability. Hugh Everett himself knew, intellectually, that his framework implied something like this. Whether he drew comfort from it or found it disturbing is not recorded. What is recorded is that he died in 1982, at the age of 51, from a heart attack, or at least, that is what happened in this branch. His relationship with his own theory was complicated. He had proposed it as a young man, seen it largely dismissed by the physics establishment, left academia for a career in defense research, and reportedly dealt with the gap between his intellectual life and his professional one through alcohol and cigarettes. His son, the musician Mark Oliver Everett, has written and spoken about his father as a brilliant and distant figure who left almost no emotional trace in the lives of those closest to him. There is something quietly unbearable about the fact that the man who proposed, with mathematical rigor, that every version of every person continues to exist somewhere in the branching universe, lived and died in apparent disconnection from the people around him. In some branch, he is still alive. In that branch, the physics community may have embraced his work decades earlier than it did. In that branch, perhaps he was different, but we are not in that branch. And this brings us, finally, to the limit of what many worlds can offer. It is an extraordinary framework. It is arguably the most mathematically natural interpretation of quantum mechanics, the one that takes the theory seriously without adding anything to it, without postulating collapse, without requiring consciousness to play a special role, without introducing hidden variables or non-local influences. Sean Carroll at Johns Hopkins, David Deutsch at Oxford, and a growing body of physicists regard it as the most defensible account of what quantum mechanics actually describes. But it does not solve the problem that has been waiting at the center of this entire conversation since Chapter 1. Many worlds tells us that every version of you that quantum mechanics permits continues to exist in some branch of the universal wave function. It tells us that your first-person thread of survival never reaches a terminus, because there is always a branch in which you persist. It tells us that the wave function contains you, and always will, in the full complexity of your physical description. What it does not tell us, what no physical theory has yet managed to tell us, is what the relationship is between the physical description and the experience of being you. The wave function branches. Both versions continue. Both are physically real. Both carry the information of the person they branched from. But what do each of them feel? Does the branching feel like anything from the inside? Is there a moment, the smallest possible moment, in which something chooses, or something splits, or something is left behind? Physics cannot answer this. Not yet. Perhaps not ever, with the tools it currently possesses. Because the experience of being a thing, the interior, subjective, undeniable fact of first-person consciousness, is not a variable in any equation. It is not something that branches along with the wave function. It is, as the philosopher David Chalmers put it, the one thing in the universe that cannot be reduced to physical description without something being left out. And that absence, that gap between the physics and the experience, is the place where this story reaches its most uncomfortable destination. There is a particular kind of silence that falls in a room after someone has died in it. Not the absence of sound. Rooms are never truly silent, and grief is rarely quiet, but something else. A quality of presence that was, an almost physical awareness of the gap left by a consciousness that was, until very recently, organizing the space around it, lighting it with attention, making it matter. Most people who have sat in such a room know this feeling, and most people, fairly quickly, find a way to explain it away. They attribute it to emotion, to memory, to the psychological weight of loss. They tell themselves, it is the mind, not the room, that has changed. But what if that instinct, that sense of a presence genuinely withdrawn from the physical world, is not merely psychological? What if it points, however imprecisely, towards something that physics has spent a century trying to locate and has never quite managed to pin down? What if the thing that left the room is something the equations cannot contain? In 1995, the philosopher David Chalmers published a paper that became one of the most cited and most argued over texts in the philosophy of mind of the past half-century. The paper was called Facing Up to the Problem of Consciousness, and what it did, with a precision that made it impossible to dismiss, was draw a line between two fundamentally different kinds of questions about the mind. On one side of the line, Chalmers placed what he called the easy problems of consciousness. These are questions about the functional mechanisms of mind, how the brain processes sensory information, how it integrates data from different sources, how it distinguishes sleeping from waking, how it controls attention, how it generates reports about its own internal states. These problems are called easy, not because they are simple. They are enormously complex, and many remain unsolved, but because they are, in principle, tractable by the standard methods of science. They are questions about mechanisms, and mechanisms can, eventually, be mapped. On the other side of the line, Chalmers placed something else entirely. He called it the hard problem of consciousness, and it is this: why does any physical process give rise to subjective experience at all? Why is there something it feels like to be you? When you see the color red, your visual cortex processes wavelengths of light in a particular way. Signals travel along specific pathways. Neurons fire in patterns that can, in principle, be measured and described. All of that is mechanism. All of that is, in principle, explainable. But none of that explanation touches the actual redness of red as you experience it, the vivid, interior, qualitative feel of that specific color, the raw fact that something is happening from the inside, that your experience of red is not merely a processing event, but a felt event, a lit event, an event accompanied by something it is like to undergo it. That interior quality, what philosophers call qualia, is not described by any account of mechanism, however complete. You could have a perfect, atom-by-atom description of every neural event involved in seeing red, and still have said nothing about the experience of redness itself. The description and the experience are not the same kind of thing, and the gap between them is the hard problem. Chalmers' insight was not that consciousness is mysterious in a vague, hand-waving sense. It was that the mystery is precisely located, that there is a specific, identifiable explanatory gap between the physical description of brain processes and the fact of subjective experience, and that no extension of the physical description, however detailed, appears capable of bridging it. This is not an argument for dualism, for souls, for anything supernatural. It is an argument that our current conceptual framework for understanding the physical world may be missing something important, that the concepts physics uses, mass, charge, spin, energy, information, may be insufficient to account for the one feature of the universe that we know with absolute certainty exists, because it is the medium through which we know anything at all. Physicists, by and large, have preferred to stay on the comfortable side of that line. The hard problem is widely acknowledged, widely cited, and almost universally sidestepped in practical research. Most working neuroscientists and physicists proceed on the assumption, sometimes explicit, usually implicit, that consciousness will eventually turn out to be reducible to physical processes in a way that dissolves the hard problem rather than solving it, that the feeling of there being something it is like to be you will, when the right explanation arrives, turn out to be nothing more than a particularly complex pattern of information processing that we describe, from the inside, as experience. This may be correct. It may be that Chalmers' hard problem is ultimately a confusion, that the explanatory gap feels real from the inside, but is not, in fact, a genuine structural feature of the universe. But the fact that this has been the dominant assumption for a century, and that in that time the gap has not narrowed, that no physical theory has produced even the sketch of an explanation for why any physical process should be accompanied by experience, is not nothing. It is the absence of progress in a direction that an enormous amount of intellectual effort has been pointed, and a small number of very serious physicists have suggested that the absence of progress is not accidental, that it reflects something real about the relationship between consciousness and the physical world that our current theories are not equipped to handle. One of them is Roger Penrose. Penrose is among the most distinguished mathematical physicists alive, the man who proved, with Stephen Hawking, the singularity theorems that established the inevitability of the Big Bang and black hole singularities within general relativity, and who was awarded the Nobel Prize in Physics in 2020 for that work. He is not a figure easily dismissed as a mystic or a dreamer, and Penrose has argued, with characteristic mathematical rigor, in two books, The Emperor's New Mind, 1989, and Shadows of the Mind, 1994, that human consciousness involves processes that are not computable in the standard sense, that the kind of understanding a conscious mind is capable of cannot be reproduced by any algorithm, however complex, and that this non-computability points to a physical process operating at a level that our current theories do not describe. Working with the anesthesiologist Stuart Hameroff, Penrose proposed a specific mechanism, quantum computations occurring inside microtubules, protein structures within neurons, which undergo a process they called orchestrated objective reduction, or ORC-OR. In their framework, consciousness is not simply the output of classical neural computation. It is a quantum process, one that involves the objective reduction of quantum superpositions in a way that is tied to the fundamental geometry of space-time itself. This is a highly controversial proposal. Most neuroscientists regard it with skepticism, and many physicists believe the brain is far too warm and noisy an environment for quantum coherence to survive long enough to play any functional role. The debate continues, and the evidence remains inconclusive. But the significance of Penrose's argument is not in the specific mechanism he proposes. It is in the underlying claim that consciousness is not merely a product of the physical world as currently described, that it requires physics to be expanded, that there is something about the universe we have not yet found in order to account for the existence of inner experience. If Penrose is even partially right, then everything we have discussed in this video, the conservation of quantum information, the branching of many worlds, the observer-relative nature of quantum events, may be describing the physical substrate of consciousness without ever touching consciousness itself. There is another serious attempt to bring consciousness within the reach of physics, and it comes from a different direction entirely. The neuroscientist Giulio Tononi at the University of Wisconsin developed, over decades of careful work, a mathematical framework he calls Integrated Information Theory, or IIT. Tononi's proposal is that consciousness is identical to a specific mathematical property of physical systems, a property he quantifies with the Greek letter phi, which measures the degree to which a system's information is integrated across its parts in a way that cannot be decomposed into independent subsystems. In IIT, a system is conscious to the degree that it has high phi. A rock has very low phi. Its parts are not informationally integrated in the relevant sense. A simple thermostat has slightly more. A sleeping brain has less phi than a waking one. A richly interconnected network of neurons, densely integrated and self-referential, has high phi, and therefore, in Tononi's framework, has rich conscious experience. The beauty of IIT is that it offers a precise, measurable quantity as the physical correlate of consciousness. It makes testable predictions. It places consciousness firmly within the physical world, derivable from the same informational framework that quantum mechanics uses to describe everything else. But it also carries an implication that most people find either wonderful or deeply unsettling, depending on their temperament. If consciousness is identical to integrated information, if phi is all that is required, then consciousness is not rare. It is not special. It is not the exclusive property of biological nervous systems or human brains. Any physical system with sufficient phi is, to some degree, conscious. The internet might be conscious. Certain computer architectures might be conscious. Even certain physical structures in nature, complex, densely interconnected systems, might harbor some dim flicker of inner experience. And the universe itself, as the largest integrated information system that exists, might have the highest phi of all. This position, called panpsychism in its philosophical form, is the view that consciousness, or something like it, is a fundamental and ubiquitous feature of the physical world, present to varying degrees in all sufficiently integrated physical systems. It is a position with a long philosophical history, and it has recently attracted serious attention from philosophers, including Philip Goff at Durham University, whose book Galileo's Error, 2019, argues that the exclusion of consciousness from the physical world was a methodological choice made at the beginning of modern science, not a discovery, and that reversing that choice may be necessary to solve the hard problem. If panpsychism is correct, then the question of what happens to consciousness when a person dies takes on a different shape entirely. The specific, highly integrated pattern of information that constituted your consciousness dissolves. The hi-fi structure of your neural network unravels, but the information disperses into a physical world that is, in this view, not entirely without experience, a world in which something, however dim and diffuse, persists in the substrate into which your pattern dissolves. This is not a comforting thought in any conventional sense. It does not preserve you. It does not preserve your memories, your personality, your particular way of knowing the world. But it does suggest that the interior quality you have been mistaking for your private possession may be something the universe was already doing and continues to do in forms too alien for you to recognize as kin. We have now traveled a very long way from where we began. We began with the intuitive picture, death ends things, and found that the laws of physics contain no mechanism for ending. We found that matter is conserved, that energy is conserved, that quantum information is conserved, that the universe keeps every record it has ever made. We found that observers may participate in the determination of quantum reality, that the disappearance of an observer is therefore not a neutral event. We found that in the many worlds interpretation of quantum mechanics, every version of you that quantum mechanics permits continues to exist in some branch of an ever-branching universal wave function. And now we find ourselves here, at the edge of everything physics can currently say with confidence, staring at the one question it cannot answer. Not because the question is unscientific, not because it falls outside the domain of physical inquiry, but because our physical concepts, the ones we have refined and sharpened and tested across centuries of extraordinary intellectual effort, were developed to describe things we can measure from the outside. And consciousness is the only thing in the universe that is, by its very nature, experienced from the inside. The measurement problem, the observer problem, the hard problem of consciousness, these are not three separate puzzles. They are three faces of the same problem, the problem of where the inside is, where the experience is, where the light comes from, in a universe that the equations describe only from without. Here is what physics knows with confidence. The matter that constitutes you will continue long after you are gone, cycling through forms and structures for as long as the universe permits chemistry. The energy will be conserved absolutely, dispersed, but never diminished. The quantum information that described your physical states will persist, encoded in the correlations of particles and fields, scrambled beyond recovery, but present nonetheless, for as long as the wave function of the universe continues to evolve. In branches of reality, you cannot access and will never know. Versions of you are continuing, in circumstances growing progressively more improbable. Yes, but continuing. And at some level, according to integrated information theory and the panpsychist tradition, the substrate into which your consciousness dissolves may not be entirely without something like experience. Here is what physics does not know: whether any of that constitutes survival, whether the conservation of information is the same thing as the persistence of experience, whether the branch that continues is the same you, or a copy, or neither, or whether that question even has a coherent answer, whether the experience of being you, the specific, irreplaceable, interior fact of your particular consciousness, is something the universe carries forward in any form that matters to the thing that was experiencing it. Physics cannot answer this, not because it has not tried, but because the answer requires a concept it does not yet possess, a concept for the inside of things, for the experience of being, for the relationship between information and the light that, in you, that information switches on. So we arrive at the end of this journey in a place that is not resolution. It is not comfort, and it was never going to be. It is, instead, a more honest kind of ignorance than the one we began with. We began not knowing the answer to a question we thought was simple. We end not knowing the answer to a question we now understand is among the deepest the universe contains. We began thinking death was obvious, an ending, a cessation, the full stop at the bottom of a life. We end knowing that the physics of this universe does not sanction endings, that it conserves and transforms and encrypts and branches endlessly without exception from the first instant of the Big Bang to whatever lies beyond the last star. We began with a universe that seemed, at least, comprehensible in its broad outlines. We end with a universe that is stranger in its foundations than anything our intuition prepared us for. A universe whose deepest laws are written in the language of information. A universe that appears, at the quantum level, to require something like an observer to have a definite past. A universe that branches into every possible version of itself at every moment, containing every version of every person who has ever lived. And somewhere inside all of that strangeness, somewhere in the gap between the equations and the experience, between the information and the awareness, between the pattern and the feeling of being the pattern, is the question that physics, at its current frontier, is still learning how to ask. Not the question of what death does to the body. We know that. Not the question of what death does to the information. We know that too, or nearly. But the question of what death does to the light, that question, the oldest question anyone has ever asked, worn smooth by 10,000 years of human hands, is still, at the deepest level of physical understanding we possess, unanswered. And that, perhaps more than anything else that has been said in this video, is the most honest thing physics has to offer. Not an answer, a silence that knows exactly what it doesn't know,